So our next talk is by Dirk Erhard from Federal University of Bahia. He's going to talk about random walk in a field of weakly killing exclusion particles.
Okay, so well, first of all, thanks for the invitation. I was really happy to receive it. And yes, so I will now talk about the work that we recently finished with Martin Heira called Random Walk in the Field of Weakly Killing Exclusion Particles. And well, this has been a work, well, that has been going on for many, many years. So some of you maybe heard already talk about it, but there will be also some new things. So some aspects will be new. Okay, so let's get right into it. So let me describe the model. And actually, the model is relatively simple. It has only two ingredients. On the one hand, the simple symmetric exclusion process, which we call eta, and on the other hand, simple random walk X. So I suppose that most of you know what's the simple symmetric exclusion process, but well, for those who don't, I will simply describe it in 2 minutes. So the simple symmetric exclusion process is, first of all, an interacting particle system. And what you consider there is really a collection of simple random walks that essentially move independently of each other, however, respecting, of course, the exclusion rule. And this means that two random walks are never allowed to be at the same site at the same time. Yeah? So if these exclusion particles really perform simple random walks, they really don't really feel the presence of each other unless they're distance one of each other, So what we know about this process is that essentially all its invariant measures are product Bernoulli with some fixed density rho. And so what we do in our model, we take the simple symmetric exclusion process, started really from its invariant measure, which has been product Bernoulli with parameter rho. Okay, so now you have these two ingredients, the simple symmetric exclusion process and the simple random walk, and now you want them to interact in some way. And well, the interactions, the kind of name is already suggesting it, is that you have your random walk, it's walking around, and every time it meets an exclusion particle, it is at risk to get killed. And it will be killed simply at rate epsilon. Yeah? And so here epsilon is the parameter of our model that, of course, we will send to 0. And the quantity of interest, the thing that we really would like to understand is what is the probability that the random walk survives given the evolution of the exclusion process. Yeah? So this probability is really kind of random in the exclusion process. So in particular, we have here this rate epsilon that really will go to 0. So the killing becomes weaker and weaker and weaker. And really what we like to know is kind of at which space time scale do we need to look at to see the effect of this killing really happening. Yeah. So that's really already the model. And I mean, these kind of models are kind of, well, be well studied in probability theory. So I guess maybe the first studies were somewhere around the 70s by Baradan and his co-authors. And what they did there is really, instead of taking as an environment in particle system, they took a static environment. So essentially product Bernoulli everywhere. So you had essentially a field of independent traps. Yeah. And so this is so-called static case. The case where the traps also evolve in time is actually much more recent and much less is actually known. And so I would like to talk about here shortly about the work that's probably the closest related to the thing that we did. So in the work that is closest related, they, as an environment, didn't take the exclusion process, but they took essentially a collection of independent random walks. So you have a collection of independent random walks. And what is the starting distribution is also the invariant measure of this system, which is product Poisson with a fixed mean rho. Yeah. So how does this model then work? Essentially in the same way as our model works. So you have the random walk on the one hand, you have these Poisson walkers on the other hand. Yeah. And at each time, essentially, the random walk will count the number of Poisson walkers. Let's say there are 5, then the killing rate would be 5 times epsilon. So the killing rate is really the number of Poisson walkers that share the site with the random walker times epsilon. Yeah. And this work by this, well, Chinese team by Shen, Song, Stu, and Shu. So they restricted themselves to the case of dimension 1. Yeah. And what they figured out is if you set the killing rate epsilon to 0, the time scale to look at is of the order epsilon to the minus 4/3. If you look at this time scale, then kind of you see the effect of the killing entering the game. And then what they figured out is in this specific case, the survival probability is of this order, exponential of minus epsilon to the minus 1/3 rho times tau. Okay. And so one thing to observe here is, I mean, first of all, okay, there are really no correction terms. So the survival probability is really of this order up to some kind of random constant. So there are really no lower order terms. And what you will see naturally appearing here is really this constant rho, right? Which is the parameter of the environment. Okay. And so essentially, yeah, essentially we do the same thing. However, we are more interested in the higher dimension situation. So what we did is, well, or what we showed is the following result, which I will shortly read to you and then I will explain. So we focus here on the dimension d equal to 3, and we take this value beta, which is actually 2, and can also be written as 2 over 4 minus d. I will explain in a second why I write 2 in such a complicated way. And what we do is then we restrict the random walk and the exclusion process to a torus of a growing length epsilon to the minus beta. What our resultant says that given the realization of the exclusion process, if you look at a time scale of order epsilon to the minus 2 beta, which is epsilon to the minus 4, then the survival probabilities of the order s tau epsilon, which I wrote down here. Okay. So let's have a careful look at this. So first of all, let's look at the exponential. So the exponential, you really see 3 terms. You see kind of the leading order term, which is this epsilon to the minus 3 times rho times tau. Then there's a constant c times epsilon to the minus 2 tau plus some constant c bar times epsilon to the minus 1 tau. So here, this constant c and c bar are really constants. We essentially have an explicit formula in terms of convolutions of discrete heat kernels. Yeah. So that's kind of the leading order term. And then there's this epsilon factor here in front of it. And this alpha 3, again, is some constant that is a convolution of discrete heat kernels. So it's rather explicit. So if you look carefully at this funny epsilon to the alpha 3 tau, it's really some kind of a log correction that you have here. Yeah? So this is really what is happening. Okay. So why was I writing this beta in this kind of funny way? I could have just written 2, right? This would have been much easier. Well, the thing is, we think that this should be kind of the general exponent. And it also shows, for instance, that in higher dimension, you can't really expect such a result to hold. So if one does the calculations of beta, so let's check. So if you take this formula 2 over 4 minus d, for d equal to 1, then this should be 2/3, right? For d equal to 1 is 2/3. For d equal to 2, it should be simply 1. For d equal to 3, it's 2. And if d is 4, well, then you divide by 0, so then it's infinity. So this kind of really suggests that something special is happening in dimension 4. So if you think about it a little bit, d equal to 4. If you think a little bit about it, it actually makes perfectly sense. So let's imagine that in dimension 4, this result somehow formally holds. What would it say? Well, it says that then in order to see the effect of the killing happening, you need to look at a time scale which is epsilon to the minus 2 times infinity, for epsilon going to 0. So actually, it really means that when in dimension 4, you need to look at an infinite time scale to see the effect of the killing happening. And this makes perfect sense, right? The higher the dimension, the more flexibility the random walk has to escape from the exclusion particles, right? Whereas the lower the dimension, well, there's often not much escape. So let's focus now on this dimension 1 because there's another result. So in dimension 1, this value of beta is 2/3. So this epsilon to the minus 2 beta would be epsilon to the minus 4/3. Yeah. If you compare this result by this Chinese group, it's really literally the same. It's really the same. So this result is kind of very consistent with the result of this Chinese group. Okay. so this is the presentation of the results. So maybe one thing that is not completely clear, what do I mean of order S tau epsilon? Of order really means that if you take the survival probability and you divide it by this S tau epsilon and you send epsilon to 0, then it converts to some non-trivial random variable. Yeah, that's really what of order means. Okay. The way I formulated the results, even though it only holds for dimension 3, of course, suggests that we also conjecture to hold in dimension 1 and 2. So in dimension 2, if it would be true, our analysis shows that then the survival probability in leading order should be of this order. You have an epsilon to the -1 here, and there will be a log correction term. In dimension 1, the survival probability will be really essentially of the same order discovered for the other case of this Chinese group without any correction terms. So in dimension 2, actually, our analysis just fails. I will comment more on this. In dimension 1, I guess it should be true, but we never wrote it down. Okay. Okay, so so that's the result. I'm not sure if you have questions about it. So then not. In the next 2 slides, what I would like to explain is kind of why beta should be of this form. This actually follows from a relatively naive scaling argument. So there's really not much behind this. And I would like to present it. Okay. Taking a little bit to load. Okay. So how can you guess the scaling? Well, so the first thing that you need to know is that there's actually a formula for the survival probability. And the formula for the survival probability, the formula I wrote down here. So here you have an expectation of the random walk with respect to the random walk starting at 0 of the exponential of minus integral from 0 to t of eta x. Yeah? So this is the formula for the survival probability. Now what do we want to do? Well, I mean, so this would be survival probability if the killing would happen at rate 1. Yeah. So now what do we want to do? Kind of we want to introduce some kind of rescaling, right? The killing should be at rate epsilon, and then we want to look at this rescaling of space and time. So now, I mean, what you can do is really, well, there are 2 objects here. There's the random walk and there's the exclusion process. So what you can now try to do is to try to rescale the random walk and the exclusion process. Yeah. So let's do this. For the random walk, well, I mean, we know how to scale random walk such that it converges to Brownian. I think I just lost internet connection with my tablets. Still here. So let's see. Let's see if it comes back. If not, then I will continue without my tablet. Let's try. Okay, let's try here. Just 1 second. Okay, now it doesn't work. So let me just share my screen. Okay. Okay. Sorry. Okay. Yeah, sorry that this happened. Okay. What I'd like now to show is really how you can kind of guess the scaling. And well, I mean, first of all, what we know is we know how to rescale the random walk, right? So the next thing that you need to figure out is how you can really scale the exclusion process. And well, what is known is that if you take a smooth, compactly supported function f, and you define this functional here, then this functional converges to a Gaussian process. So let's have a look at it to try to understand. So what do we have here? Here we have 1 over 2 to the nd half times the sum over all x and z f of 2 to the minus nx times the exclusion process at position x at time 2 to the 2nt minus rho. So, I mean, first of all, what you really have here is here you do a recentering of the exclusion process, right? And then now you have this function f. This function f is a function that's compactly supported. So this means if 2 to the minus n times x is of order much larger than 1, well, f simply becomes 0. Yeah? So the terms x in the sum that really contribute to the sums are all that are such that x is of the order more or less 2 to the n. So the number of points in the sum is 2 to the nd. So what you really see here, that in front you really divide by the square root of the number of points in the sum. So this is really a central limit theory. Of course, also makes sense since the limit is Gaussian. It's a central limit theory. So this is nice, and there's actually a smarter way of rewriting this. So instead of dividing by the square root of the number of points in this sum, I can also divide by the number of points in this sum. Yeah? If I do this, then I need to blow up the exclusion process by this factor 2 to the nd half. So I mean, I really haven't done anything, right? However, this is a slightly better view of point. Why? Because now, since I divide by the number of points in the sum, essentially it's a Riemann sum approximation. And it really kind of shows that the term that is random here, this exclusion process, once you blow it up by this factor in front, then it really converges to some kind of random Gaussian field. So what you really should do is you really should blow up this exclusion process in this way. So if you do this and you plug everything into the formula for the survival probability, what you really get is something like this. And then you are essentially almost done. You do a change of variables. Yeah? So now time runs until time 2 to the n times t, and you get this volume factor 2 to the minus 2 n in front. Yeah? And then all the rest that rests to do is to call this factor in front of the integral epsilon. And it turns out that if you do the calculation, that 2 to the 2n is equal to epsilon to the minus 2 beta, with the value of beta announced. Yeah? And well, that's how you kind of guess the value of beta, and it turns out that it's really the correct thing to do. Okay, so this is essentially about the result. So how do you do the proof? Well, so the proof is actually based on the fact that this survival probability, you can relate it nicely to the so-called parabolic Anders model. So it's almost the same. And then essentially what we're doing, we want to rescale the random walk and we want to rescale the exclusion process. So what we really do is we try to rescale this equation. Yeah? And then you expect that you see some kind of continuous equation in the limit. And so this then really nicely fits into the framework of the theory of regularity structures, at least in dimension 2 and 3. In dimension 4, it simply breaks down. Which also, right? Because we saw that in dimension 4, actually, this value of beta is formal infinity. So you really wouldn't expect anything nice to happen. Okay. And so again, so the proof is really based on that. And really, what is the big challenge here is to understand how the exclusion process really converges to its limit, right? Because in a sense, this equation is some kind of a function of the exclusion process. And if the exclusion process were already Gaussian from the very start, then actually everything goes through pretty smoothly with not so much effort. Yeah, but well, as you know, the exclusion process is not Gaussian, it's Gaussian in a limit, but for each fixed n, it's not really Gaussian. And essentially, you need to find a way to quantify how close is it in some sense. And there are, of course, several ways of doing this. In this framework, looking at so-called cumulants is actually the right way. I essentially forgot everything I said. So here's the definition of a cumulant. So if you've given a random variable x, its cumulants are given by the coefficient of the log generating function k of t that I was writing down here. So the logarithm of the expectation of e to the tx. So you can try to do a power series expansion of it. And these funny kappa n in front here, these are what are called the cumulants of the random variable x. The nth cumulant of the random variable x. Okay. So let's give you an example. So if x has a Gaussian distribution, say with mean mu and variance sigma squared, then it's pretty straightforward actually to compute this cumulants, right? Because in this case, we can compute the x expectation pretty precisely to obtain this term. And from this, you can really read off the cumulants. So in this case, it really turns out that the first cumulant is equal to mu to its mean, and the second cumulant is equal to sigma squared. And so you see that in the exponential, there are no higher order terms, which implies that all higher order cumulants are simply zero. Yeah. And now you can look at it. You can calculate the cumulants of other distributions. You will always find that the first cumulant is equal to the mean, the second to the variance. And now you can ask yourself, well, I mean, how many distributions are there such that all the cumulants of order 3 or higher are zero? And it turns out there's exactly one, the Gaussian distribution. Yeah? So in this way, you can kind of get a feeling how much Gaussian a certain distribution is or not. So to the best of my knowledge, I think they even proved the central limit theory using this fact. So what does this suggest? So this kind of suggests that one smart thing to do maybe is to try to get a grasp of the higher order cumulants of the exclusion process. Yeah. And this is essentially the main part of the work. So I will present now the estimate that we have. So unfortunately, my tablet doesn't work. Otherwise, I could explain it a bit better, but let's see. So one of the key estimates in this work, and essentially most part of the paper is really dedicated to this, is the estimate I wrote down here. So I will read it and then I will try to explain. So we fix some dimension d at least 3. Then what we do is we fix k space-time points. And for any collection of k space-time points, there exists some constant c that only depends on k, such that the joint cumulant of the unrescaled exclusion process satisfies the estimate I was writing down here. Okay. So what do we have here? Here with the sum over sigma, the product from 1 to k, and then we have kind of this funny space-time distance here. Yeah, you see here's the 1 plus the distance between t sigma I plus 1 minus t sigma I, plus the distance x sigma I plus 1 minus x sigma I squared to the minus d over 4. So let's try to understand this a little bit. So the first thing that you see is here we have the sum over all bijections, sigma mapping the set 1, 2, 3 until k into 1, 2, 3 until k. So really what this is the sum over all permutations of the numbers between 1 and k, right? So what else do you see here? So here we always compare the distances between kind of the following points in the permutation. So really what you need to try to imagine is that you kind of write the numbers 1 to k in a circle, and then kind of you connect all the two neighboring points. Yeah. And to each of those connections, you associate this kind of funny space-time distance that I was writing down. That is really essentially what is happening. So if you look at the space-time distance, let's try to understand a little bit further. So first of all, why is there this 1 here? Well, I mean, this 1 is here because we allow, of course, also the case that t sigma I is equal to t sigma I plus 1 and x sigma I is equal to x sigma I plus 1. If the 1 wouldn't be here, we would divide by 0 and it would be infinity. But the exclusion process is bounded, so we don't need to estimate by infinity. The second thing that you see here, if you compare how the distance in time is measured compared to how the distance in space is measured, well, the distance in space you square and distance in time you don't square. If you think now about the heat kernel of Brownian motion, then there's also something that is happening there, right? There you have the exponential of minus x squared over t. And what this estimate, what we think that this estimate is more or less optimal, if this space distance is roughly equal to this, if this space distance is roughly equal to the time distance. Yeah? You can, for instance, check in the case k equal to 2, in the case that t sigma I minus t sigma I plus 1 is of the order x sigma I minus x sigma I plus 1 squared. Yeah? In the case k equal to 2, then this would essentially give exactly the estimate you would get from the usual heat curve. Yeah? So this really suggests that this estimate is probably relatively optimal. Okay. So again, so this estimate is probably the key estimate in our paper. And if we would have the same result for d equal to 2, then the result would simply be true. So there would be no problem about that. So that's really, yeah.
Sorry, can I ask a question?
Yes.
You have there is sort of a permanent, right?
I wouldn't interpret it like, yeah, but there are no sign changes, right?
Yeah, exactly. That's why it's a permanent. You remove the -1.
Okay. Good. You're right. Yes.
Can you say something about that? How that comes up?
Okay, so let's see if this really answers your question. So one way I tried to explain it is that you kind of you imagine that these kind of k space-time points are aligned around the circle, and then what this permutation does really, kind of you connect all these points in one circle. Yeah. So its circle is what? It's a connected graph, right? And this was actually the key point, that we can kind of estimate the cumulant in terms of something that you can relate to a connected graph. If you would kind of do the naive estimate, so if you see there's a combinatorial formula of the cumulant, if you would kind of apply a naive estimate of it, you would get something similar. However, something that would consist of several connected components. And the point here is that here we talk only about one connected component. I'm not sure if this has maybe something to do with the permanent business. I don't know. It's not really. Oh, okay. Okay. And okay, so that's kind of probably one of the key results in this paper. So now let me wrap up. So the 25 minutes are essentially over. So what are kind of the next challenges? I mean, clearly the result should be extended to d equal to 2. Yeah. Then there was some kind of artificial condition in the result, which probably can be removed. It's a little bit of work. It's more technical work, but I think there's no big conceptual challenge. Is to look at the exclusion process and the random walk on the whole space instead on the torus. And well, so the biggest challenge is for sure lift this restriction that you start the exclusion process from its invariant measure. So this is something that we really use throughout the paper. Without it, I think this estimating the cumulant would simply fail. Well, at least we would not be able to say much about it. Okay, thanks. Thank you very much.
Okay, let's thank Dirk for the nice talk. Is there any question for Dirk?
I have a question, Milton.
Yes.
So I don't know if you said it, but I guess in the random walk environment, in other dimensions, the answer should be the same with the same beta?
Yes, exactly. That's why I was formulating this kind of funny way. I mean, otherwise
that's not known. It's only conjecture.
Yes. So I think in dimension 1, I'm pretty sure that this is true. Dimension 1 is it's a different context. You wouldn't use regularity structure for this, but it should be definitely true. In dimension 2, I'm also pretty convinced that's true. So essentially, our proof really only fails by an epsilon, or yeah. So actually, we know exactly what is kind of missing, and I would be extremely surprised if it wouldn't be true.
Yeah, and in your sort of guess for the scaling, it didn't quite depend on the exclusion process, right?
Yeah, exactly. Exactly, exactly. I mean, so the only thing that you really see is that in dimension 4, something special must happen, right? Because then you divide by 0. Yes, yes, yes. It didn't really depend on the exclusion process. That's why this kind of shows that this is probably the right argument, because this kind of Chinese group, they look at the different processes. Actually, it's essentially the same scaling limit, and the resultant d equal to 1 is very consistent.
Okay, thanks.
Okay, so any other question? So,
I'm sorry.
yes.
Can you give any intuitive explanation of what breaks down in dimension 2, or is due to some?
It's a technical, essentially it's a technical problem. So computing, we're estimating these cumulants are not very easy. So we didn't get a handle on this log generating function, but there's some kind of combinatorial formula which kind of relates cumulants with moments. And this is really an alternating sum.
Mm-hmm.
And then you really need to essentially to estimate the moments from above and from below in a very fine-tuned way. And the exact moment where it breaks down is, so at some point in the analysis, what you really need to analyze is you look at an exclusion process only with n particles. Yeah? So really only n particles. And now you're essentially interested in the transition, in this kind of joint transition property of these n exclusion particles, starting at, well, n different locations and then ending up in n different locations. Yeah. What we know for that, at least as an upper bound, we have some kind of sort of Gaussian upper bound. And this is enough to push the result through in dimension 3. However, what we actually would need, we would need to have some kind of local central limit theorem for gradients of these n exclusion particles. And this is something that is missing. So the best way we could do is bound this kind of gradient by the sum, which is of course pretty bad.
Sorry, I just missed
anything
it.
that
you need a local central limit theorem or what?
Yeah. So you look at the exclusion process of n particles.
Mm-hmm.
Then you can now calculate the probability that these n particles start at n different locations, end up in n different locations. And you can ask yourself, what is the probability for that? Right? And you can ask yourself, well, is there some kind of a local central limit theorem in the way that this transition probability can be written like as a product of n Gaussians? Fair question. Yeah. And it turns out, yes, at least as an upper bound, this is true. But now if you want to have something, and this is enough for dimension 3, but for dimension 2, we would need a little bit more. We don't only want to look at kind of at this transition probability, but kind of at differences of this transition probability, discrete gradients. And as far as we know, there's nothing in the literature. But if we would have anything that would estimate the gradient by something that's a little bit better by replacing the minus in the gradient by a plus, then the resultant dimension 2 go through.
Okay, thank you very much.
You're welcome.
Okay, so if there are no questions, let's thank Dirk again.